line, surface, or volume. So they can be represented as algebraic equation or they can be represented using parameterized vector. So how to and fro means how uh, these two technologies, algebraic equation and parametric vector, now how we can make kind of intercommunication or exchanging them if or converting them from one form to other form. Anyway, we have seen vector field. So vector field is nothing but when we have a point x comma y comma z, at that point then we have a function that generates a vector. This is vector field. We will coin a new term called flow line. So vector field, flow line, algebraic equation, parameterized vector. So these are the things that we will see. So if I have a line, then line has a algebraic equation. If I have a line, then it may have parametric vector equation, where parametric vector is a vector where algebraic equation is inserted with only one independent variable, that is t. Okay. Now, if I have a situation where if I have algebraic equation and then now if I substitute x, y, z, okay, like suppose I have fxy equal to then function in x and y. If I pick any x comma y, okay, if I pick any x comma y, then I get the z value, that is fxy. Okay. Now, if I keep this is xy plane. In the xy plane, I have so many xy points. This is xy plane and I have so many xy points. If I have a function over x comma y, if I have a function over x comma y, that function over x comma y result in vertical value. So now we have against each x comma y we have points now in vertical. If I connect this, then it becomes a surface. Okay. Now if I have a function over x fx, then I get set of value in same xy plane. If I connect all those, it becomes a line. Line do not have any direction and line has only points. This is what I don't want. So vector field we are talking. So we have discussed, like if I have a magnetic field, then magnetic field, if I keep the compass needle everywhere, then compass needle points in one direction. So at each point I keep the compass field, then compass field show a direction. So at each point we have a vector. So earlier at each point, if it is a kind of a line, then at each point we have a algebraic equation. Now at each point we have a vector, that is vector field. Okay. So what is algebraic equation? If I have a function over fxy, then fxy against each x comma y, I can have an altitude, that is z, or I can have density function. This is what we know. But at each x comma y, if I have a kind of a vector, if fxy results in a z value or fxy result in a density function, then we call it as algebra. Okay. If fxy, capital F, earlier in algebra fxy is small f, now fxy is capital F. So when it is capital F, then against each x comma y we have vector. This is vector field and this is what we exactly see in the magnetic field. If I have, okay, somewhere I had, if I really have a kind of two two magnets. If I really have two magnets and I keep one magnet here and one magnet here, north and south pole, then if I place the compass north pole of the magnet here and south pole of the magnet here, if I place compass, the needle would be always this direction. But if I make a curve and keep the compass, the needle will move here and there the way it should feel. So the at each point, at if this is xy plane, then at each x comma y, at each point x comma y, then we have a vector. So fxy, capital F, on top of which there is arrow. So this is a vector field. Small f xy, it is a function over xy. Capital F xy and arrow, this is also a function over x and y. But this function generates a vector. Earlier function, either it generates an altitude, that is called z, or it generates a density in the xy plane, different density based upon the x comma y. Now we have here here we have okay. Now here we have at each x comma y we have separate vectors. So this function capital F over x comma y generates a vector at x comma y. Example for this can be like if I take fxy equal to 3i plus 4j, fxy equal to 3i plus 4j. If that is the case, then if I take any x comma y, it will generate out at that point. If this is xy plane, if this is xy plane, at any x comma y, at any x comma y, if I apply this function over it, it generates a vector there. Okay, so if this is xy plane, then at any x comma y, at any x comma y, there is a vector. I mean, x comma y is the bottom, and from there will be a vector. X comma y bottom, from there is a vector. X comma y is the bottom, from there is a vector. What is the direction of the vector? That is 3i plus 4j. 3i plus 4j is the direction of a vector. So all vectors are in same direction. Okay, so all vectors are in same direction because 3i plus 4j is not dependent upon any variable. So that is the scenario. Okay, so that is the okay, so that is the scenario. Now it is something like now we have suppose we have another equation. Another equation is that I have fxy capital F fxy equal to yi fxy equal to yi. So since it is I, then it will have a direction that is parallel to x-axis. Now if I take any point that x comma y, at that point, if this is x-axis and this is y-axis, the function over fxy is yi, then at any point I take at that point vector would be in x-axis. If this is x-axis, then vector would be in along the x-axis because it is yi. But the magnitude of the vector would be y. I is the direction and y is magnitude. So with a vector is an energy which has a direction and which has a magnitude. So if I say yi, then in along the I direction, the so if I go along the x-axis, then the vector will be of 0 magnitude because y is 0. But if we go along y-axis, then the vector will be in this direction, but the length of the vector will keep growing. So here the vector will be this small, vector will be big, vector will be big, vector will be big. As we go along the y-axis, then vector will be along the x-axis direction, but the size of the vector will keep growing because fxy equal to y. So this is vector field. At each point, at each x comma y, we have a vector. Okay. Now, question arises is that what is the importance of vector field as far as representation, in addition to representation of magnetic field or electrical field or electromagnetic field or velocity field or force field, what are the other importance of a vector field? Okay, that question arises. Now, suppose that I have a equation small f, algebraic equation, a small fx y, a small f, f is small, that is algebraic function, fxy equal to something. Suppose it is x square, it is x plus y, fxy equal to x plus y. It is a pure algebraic equation where the independent component is x and y and independent component is x and y and dependent component is fxy. Whatever fxy value comes with each independent component x and y, that is fxy. Now question arises is what is x and y when it comes to parametric vector. Now two forms we are seeing that we can show a kind of we can represent a line, surface or volume or any kind of graph, any kind of shape. We know this, that either it can be point line or it can be a surface or it can be volume. If I say fxy equal to x plus y, it is hinting towards a surface. Fx equal to, if I say y equal to fx, function over x only, then it is hinting towards a line. Fxy equal to x plus y, where function over x comma y, then it is hinting towards a surface. So now we are kind of we have a surface equation, that is x plus y. What is x and what is y when we see the parametric vector? Parametric vector, each has x component, y component, z component, whatever as per the number of dimensions, where x, y components are dependent variable. Where we see the algebra, x, y are independent variable and fxy is dependent variable. Whereas if we see the parametric vector, then x component of the vector can have many orthogonal components. Typically, it is x component, y component, and z component as its orthogonal component. If they are the orthogonal component, then what is x component? That is, x component is dependent component upon an independent variable t, and y is a dependent component dependent upon independent variable t. Z is an dependent component dependent upon independent variable t. So this is parameterized vector equation, and since it is always dependent upon only one independent variable, and since it is a vector, we address it as r. R on top of it vector sign. This is a vector. Since this is a function over independent variable t only, so in bracket R in braces t on top arrow. So this is called parameterized vector r t, function over t, on top of it an arrow. The grammar for the parameterized vector is it is set of two vectors. First vector is a point through which this vector passes through, and second is the vector that is a function over t, and that is the actual position vector. So position vector that is a function over t, and then another vector, the point through which the vector passes through. All along there are two vectors, they combine together to form the parameterized vector. Now I have algebraic equation, that is fxy equal to x plus 1, that is the equation of a surface. Then what is the parametric vector? Question is straightforward. Since there are two ways to kind of represent a line or surface, one is through algebraic equation and one is through parameterized vector, parametric vector. If algebraic equation is fx comma y equal to x plus 1, then what is the corresponding parameterized vector? What is x plus y? X, x, x. X is x component of the vector. F is small f, fxy equal to x plus y. X is x component of the parameterized vector. Y is the y component of the parameterized vector. This is how it transforms. Okay. X is independent, y is independent in algebraic equation, where fxy is dependent. Here, x component comes and it becomes dependent upon t. Y comes as y component of the vector and it becomes dependent upon the t. So here x becomes xt, x becomes a function over t. If I have algebraic equation fxy equal to x plus y, I have a parametric equation that is x component, y component, z component, whatever. Now the x in the algebraic equation transforms to x component in parametric vector. Y transforms to y component in parametric vector. X and y are independent here, dependent in fxy function. Here x, y are dependent. Independent is t. So the x component of the vector is actually x in braces t. Y is y braces t. Those are function over t. Okay. So x independent variable in algebraic function transforms to dependent variable in vector and it is a function over t. How I can calculate map the algebraic equation to the vector equation? That is the question. So algebraic equation, parametric vector equation, and then the new item comes in that is called vector field. Okay, this explanation is not available in any of the book. Only thing you will know that is the equation and vector field and parametric equation converted. Means parametric equation and here and there few examples. But what they are, why they are important and what I am going to talk now, nothing is available in any of the book. You can go and you can search. Okay. So if I have a algebraic equation of a line, surface or a volume, then accordingly same I can get as a parametric vector equation, where parametric vector equation is a hybrid model of vector and algebra, where independent component is t and it has three component x, y, z, where in algebraic equation x, y, z is independent component and there is no t, and the dependent component is fxy or fxyz. If I want to map these two, then in between I bring another thing that is called vector field. Algebraic equation transforms to vector field. From vector field, we get back the the parametric equation. If I transform algebraic equation to vector field, and from vector field I get back that parametric equation, vector field to parametric equation when we get back, then at that moment the parametric equation is called flow line. Okay. If there is a vector field, from vector field if I get back the parametric equation, then at that moment we call it that we are getting back flow line of the vector field, not the parametric vector, flow line. Even though flow line and parametric vector are same, but this is what the nomenclature is, that we are getting back the flow line. What is flow line? Why we call it flow line? Now consider that how we get the vector field from algebra. Now vector field, if I see, then it is a function which produces vector at each x, y, z. If I have different x, y, z value, at each point we get a vector. So it is a vector factory. So vector field is a vector factory. So we also address vector field is a function over x, y, z. This function returns a vector. So here in algebra, if I have a function over x, y, z, then this returns a value. Here in vector field, if I have a function that is dependent upon x, y, z, then it returns a vector, not a value. Okay, so at that x, y, z point, you can draw the vector. So at each separate x, y, z point, you will land up in drawing so many vectors which may have different direction. So this is a bunch of vector that you will get as many x, y, z point you have. That is the fundamental, that is the role or responsibility of vector field. Vector field is addressed as capital F, not a small f, capital F, function over x, y, z, or function over x, t, y, t, z, t, parametric equation, xt, y2, zt, or x component, y component, and z component of the parametric field, or rt, function over rt, anything we can say. If I come from algebraic equation, then vector is function over x, y, z, where f is capital and vector. On top we have an arrow, function over x, y, z. But from parametric equation side, x, y, z are nothing but x, y, z component of the vector, that is xt, yt, and zt. If that is true, then that becomes rt. So function over rt, that is a vector field, or function over xyz from the algebraic side, that is a kind of vector field. If from vector field, if we try to get back the parametric equation, we call it, we are getting back flow line. How we get vector field from algebraic equation? If I have algebraic equation x plus y, simple, fxy equal to x plus y, then what would be its vector field? If you see the closely the vector field, as I said, the vector field example can be fxy equal to 3i plus 4j. 3i plus 4j. Now, whatever xy you take, then it will result in a vector that will have same direction as 3i plus 4j. Or fxy equal to yi, with whatever xy point you take, the vector will be always in I direction and its magnitude will be y. So these are the typical. So vector field is an array kind of thing where the magnitude is function over x and y and z. Okay. So we can say that vector field f is a function over xt, yt, and zt. Okay, because the each term in I, if it is a, now since it is a vector field, vector, so it has three components, I, j, and k. Then each component of the vector is function over xt, yt, and zt. Means it can be x, y, z in simple terms. So it can be like fx, y, z, where f is capital vector field equal to x, y, z, x into y into zi plus x plus y plus zk plus x to the power y to the power zk, whatever. So each component of the vector itself is a function over x, y, z. That's why we call vector field f is a function over x, y, z. So vector field f can have many components since it is a vector. So if it is a 2D, then it has component f1 and f2. If it is a 3D, then it has component as f1, f2, f3. Like that, if it is a 2D, x and y, then it would result in a parametric vector RT where there are only two components x and y, xt and yt. So function vector field function f over xt yt will have may have I and j both or one of them or none of them. I and j component where x component is again function over xt yt and j component again has a function over xt yt. Whereas in parametric equation each component has a function only over t. Okay. Now how to get from algebraic equation to vector field? That is the question. Okay, now the answer is if we want separate x component, separate I component means I direction, separate j direction component, then we have to create a partial derivative. So if this is a displacement vector, this is a displacement algebraic equation, then vector field will be velocity vector field. If I create partial derivative along x-axis y, this is how we can get ith component and jth component. If I say small f algebraic equation, small f xy equal to x plus y, there is no I and j, x plus y. Then if I differentiate it along x-axis keeping y as constant, then it will become I. And if I differentiate again along the y-axis keeping x component as keeping x as constant, then it would become j. If it is a 3x plus 4y, okay, I'm sorry, if it is a 4x minus 3y, and deliberately I am taking like this. If it is 4x minus 3y, fxy equal to 4x minus 3y. If that is the case, if I differentiate it along x-axis and y-axis, then it will come as 4i minus 3j. Okay. Now if I want to get the reverse of it, then I have to get the new vector because this becomes a velocity vector. From the displacement vector field, we transform into a velocity vector. So, from the displacement algebraic equation 4x minus 3y, I transformed it to vector field that is 4i minus 3j. Since I differentiate it, it becomes a velocity vector field. Now, velocity vector field, since it is a velocity, if I integrate it, it becomes a flow line. Okay, if I say I have a velocity that is 3 kilometer per hour, 3 kilometer per hour, at the end of 10 hours, what is the distance? So at the end of 10 hours, 30 kilometer is the distance. What is the distance at the end of 5 hours? At the end of 5 hours, the distance is 15 kilometers. So if I know the velocity, then at each point, if I integrate it, then I am calculating the flow line, how it is flowing, displacement. Okay, so if I have velocity equation and if I differentiate it, I get acceleration. But if I have velocity and if I integrate, then I get the displacement at each point. That is nothing but the flow line. Or if I have something, if I can see a paper, small paper is flowing on a water, it is a velocity field. Okay, if I integrate the velocity field, then I get the displacement at each time where it is, how it is going. If I know the velocity vector at each point, what is the velocity vector? If I integrate it, then I'll get the flow line, how it is flowing. If I have a vector, if I have a magnetic field, the where the vector is like this in a path, then I can trace the path on which I kept the kind of compass needle. If this is south pole, if this is north pole, and compass needle I keep in a curve, and then okay, and then at each point I have a magnetic field. If I consider this as a velocity field, if I integrate it, then I'll get the curve equation, that is the flow line. If I have a velocity vector at each point in the direction, what is the velocity vector? If I integrate that point, I can connect, I get the flow line, that is the distance. Okay, that is nothing but the parameterized vector. So equivalent to the algebraic equation, we have parameterized vectors, but we first differentiate it along x-axis, y-axis, z-axis, partial derivative, so that I get the vector field along the I, j and k. Once I get the vector field, then I integrate it, okay, each component x, y and z, to get back the each component of x, y, z in the kind of parameterized vector. These explanations are reasoning are not available anywhere. Okay, so that is the flow line. Now I have the vector field, that is 4i minus 3j. If this is the velocity vector, then the flow line would be perpendicular to it, because it may be a curve. It may not be a straight line. If it is a straight line, then it is in same direction. Okay, since it is a surface equation. So now if it is a velocity vector, that is 4i minus 3j, the perpendicular to it would be 3i minus 3i plus 4j. 4i minus 3j perpendicular to it, another vector would be 4i plus 3j. If I do the dot product of these two, then it would lead to 0. So now I have a kind of another vector field, that is 4i plus 3j. Now I'll convert it to the kind of parametric vector. So here the xt, the x component is 4 and y component is 3. So if I integrate 4 over t, it becomes 4t. Whereas if I integrate, okay, so I believe I am right. I'm sorry, it was 4i minus 3j, the earlier one. Now, the perpendicular to it is 3i plus 4j. 4i minus 3j was the original, now velocity vector. Now, from there, I got another vector field that is perpendicular to it, that is 3i plus 4j. Now, if I convert, that is 3 is the x component, if I integrate it, then if I say, since this is the derivative one, whatever the normal algebraic equation is, vector field is a derivative one. So each component, if whatever the value, whatever the component, it has an x component, that is a differentiated one from the parametric equation. So if I have 3i, then 3 is the differentiated one. So I have to take the antiderivative or integration, come back to the parametric equation. So it will come as 3ti plus 4tj. 3i, so 3 will be integrated as 3t and 4 will be integrated as 4t. So the parametric equation or the flow line would be 3ti plus 4tj. That is this algebraic equation to vector field 2. This is a matter of research. This is not available anywhere. What, as I said, always that importance of mathematics is only when you relate the mathematics in your real life scenario. Otherwise, it has no importance. Just getting the marks in examination, it doesn't make sense to learn the mathematics. Now, if I have 3i plus 4j as vector field, then 3 is the xtyt, xt, xtyt. So 3 is kind of, I can say, the f1 component. If f has two components, f1 and f2, then f1 function over xt and yt is 3, and f2 function over xt and yt is 4. Now the f1, if I integrate the f1, then it will result in the x component of the parametric vector or flow line. So I can say now that f, capital F, rt equal to dr by dt. I have algebraic equation, I made a derivative and it came as vector field. Now vector field is both algebraic side and parametric vector side, both. Now from parametric side, if I get back the parametric side, I have to integrate it. This means that parametric equation was differentiated to get the vector field, if that is true. And parametric vector of flow line is RT, then R, and then you can say one line, that is the derivative or dr by dt is F over RT. So if I want to get dr, then I have to integrate it. Now f has component as f1 and f2. So f1 is 3 here and f2 is 4 here. So if f1 is 3, then if I want to get back the xt, then I have to integrate it, antiderivative, that is 3t. And f2 is 4, then it is 4t. Now the equation of the parametric equation is 3ti plus 4tj. Now if I say that it is passing through a point that is 1 comma 2, then it becomes 1 plus 3ti plus 2 plus 4tj. This is the equation of the parametric equation when the kind of the algebraic equation was 4x minus 3y. Now let's see closely what is 4x minus 3y. If I say 4x minus 3y is the equation of a line and if I equate it to 0, then 3y equal to 4x, y equal to 4y 3x. So y equal to 4y 3x is the equation of a line whose slope is 4y 3. Now I have in vector form 3i plus 4j. For each value 3ti plus 4tj. So for each unit of change in 3 unit of change in x brings 4 unit change along y. So dy by dx, the slope of the line is 4 by 3. Same as line equation y equal to 4 by 3x, y equal to mx, y equal to dy by dx x. So change in 3 in x brings 4 change in y. So dy by dx is 4 by 3. Same as vector equation 3ti plus 4tj. When there is 4 change, 3 change in x brings 4 change in y. But we use vector field in between because we turn the displacement algebraic equation to velocity vector, and then we did the dot product and we take out the actual vector field, that is the displacement vector field, and then we integrate it to get the flow line or the parameterized vector. We'll proceed on this. So this is something like that is commercial calculus. Now commercial calculus in the sense that if we have kind of vector field of any kind of ocean wave or anything, then we can understand the flow line. As I always say, that whatever phenomenon we are seeing through our eyes, those phenomenon, if we somehow we can place in a mathematical equation, then we can predict the future. This is what the artificial intelligence or machine learning, that whatever whatever data we carry, that data we try to parameterize in a equation, and then we change the variable and see the future. Okay, so we have tsunami and those kind of things, where if we kind of tsunami do not come in one day. Tsunami comes because there is an earthquake. Earthquake do not come in one day. If someone watches the wave, okay, inside the ocean, then wave starts changing long way, months backward, and slowly wave changes, and wave becomes this much powerful, then there is a earthquake. Earthquake is led by wave generation that starts month by, and electromagnetic waves become that much powerful that it triggers earthquake. So if someone studies the kind of wave formation, and then he can parameterize in an equation or flow line, then changing the t value, time value, then you can predict the power it would generate in next 1 month, 2 months, and 3 months. If that power grows to a limit, that it can cause an earthquake, then certainly you will have tsunami and you can save thousands and thousands of lives. So that is the importance of mathematics. So we are coming in a kind of practical, commercial or life-saving mathematics when we are in vector field and parameterized vector. Life is not easy because if you are saving thousands of lives, then you are something that you are trying to understand nature now. Nature is very powerful. Means you can just see that one if wind flows, then how much energy it carries. It uproots so many big tree that human cannot even shake it. So nature is very powerful. If you are trying to understand the nature, then mathematics will be powerful. Okay, just 2 plus 3 equal to 5 will not work. Okay, because you are trying to challenge something, you are trying to understand something that is very powerful. Okay, so we will proceed in the vector field and flow line, and we will see few example, and then we'll see cornerstone also where we cannot do the conversion. Vector field to the parametric equation of flow line that we cannot do. Then we'll see kind of some estimation. Okay, like Euler estimation is very famous. Euler used to be a mathematician and he talked about converting the vector field to parametric equation, means some set of points through which we will have the value. So those things that we will proceed on. Keep patience.